Good morning, everyone, and thank you for joining this LIFE ITS4ZEB talk. I'm Giulia Righetti. I'm from the University of Padova, and today I'd like to introduce you what I call the hidden power of phase change, so the latent heat. Latent storage is often mentioned as a promising solution, but it's also frequently misunderstood. So in this talk, I'll focus on the fundamentals, why latent storage is different from sensible storage, and why temperature is not the right variable to look at, and how these concepts translate into real systems, in particular residential heat pumps. So let me start with a very simple but fundamental question. So why do we need thermal energy storage? In many systems, production and demand do not occur at the same time. So heat is often available when it's not needed. Think of renewable sources or off-peak operation. And on the contrary, it's required when it's not available. Plus, in industrial environment, a lot of heat could be recovered instead of wasted, and this is called waste heat recovery. So thermal energy storage addresses this temporal mismatch by shifting energy in time. This enables peak shaving, load shifting, and waste heat recovery. So compared to electrical storage, thermal storage is usually more robust, especially when heat is the final energy carrier. So when the end use is thermal, like space heating, domestic hot water, or industrial thermal storage recovery, is often the most direct and efficient operation. At this point, I think it's important to distinguish between sensible and latent heat. So sensible heat storage relies on temperature variation. And the stored energy is proportional, of course, to the mass, here M in the formula, the specific heat, and this is important on the temperature difference. This implies a limitation. To store a large amount of energy, we need large volumes and/or large temperature swings. On the contrary, latent heat storages exploit a phase change. So typically is the passage from solid to liquid that occurs at nearly constant temperature. Here, the formula is different. The stored energy is proportional, of course, to the mass, but also to the latent heat of the material, not the temperature difference. This example, I think it's very illustrative because to store 10 kilowatt hours of energy, we required roughly 860 liters of water with a temperature rise of 10 kelvins. The same amount of energy can be stored in around a quarter of the volume, about 225 liters of PCM with a latent heat of about 200 kilojoules per kilogram. So this is why the latent storage is more compact and attractive for application, of course, where temperature stability is required. So this brings us to a key conceptual shift. When working with latent storages, temperature is not longer the most informative variable. We have to introduce another one, enthalpy. Because during melting and solidification, PCM doesn't use the energy to change its temperature. but energy is used to change the state of the matter from solid to liquid and vice versa. So as a consequence, temperature remains almost constant with a lot of energy, while a lot of energy is exchanged. So in practical terms, a PCM system, a latent system, can exchange a lot of energy, a lot of kilowatts of thermal power while appearing almost isothermal. So this is the reason why latent storage are described having a hidden power, because the energy flow is not visible if we look at the temperature. So for this reason, when we refer to latent storages, we have to refer to enthalpy, which represents the total thermal energy stored in the material, including the sensible and the latent contributions. So if we look at this graph, the enthalpy temperature diagram, we can see this behavior. Well, as the PCM receives energy, we have three regions. The first one is a solid region with a linear sensible behavior. So we have a temperature increment. Then we have a region, the phase change region, where a very large enthalpy variation occurs over a very small temperature interval. And finally, the third region is a liquid region where sensible behavior appears again. So temperature rise with an enthalpy increment. But typically, the great majority of the total energy shared is in the second region. So it's concentrated in just few Kelvin around the melting temperature. And this explains why temperature is not useful anymore, but also explains the strong stabilize effect of these latent storages that can have on the system temperature. So, well, the performance of a latent system depends on the PCM and on its thermodynamic properties. Here I've listed the main ones. We have the melting temperature or the melting temperature range, that's okay, that must match the operating temperature of the system. Of course, if it doesn't, the latent effect, the second region we've seen in the previous slide, it's not exploited. Then we have the latent heat that determines the energy capacity. So the larger this parameter, the larger the latent heat, the higher the enthalpy jump and the bigger the storage capacity. Then we have the specific heat and the density. They both influence the sensible contributions and the volumetric energy density. The volumetric energy density is the energy per unit volume. So it's what matters in the real systems, because it's how much energy I can store in a defined volume. Finally, we have the thermal conductivity, who determines how fast the energy can be charged and discharged. This is often the bottleneck of the latent storages that have to be enhanced with particular metal geometries and structures. So altogether, these parameters well, show that the selection of the PCM, it's not an easy decision. It's not a generic and just a material decision. It has to be integrated in the whole design system. Then it's important to be realistic. Well, we have real PCM. The ideal doesn't exist for many reasons. First of all, the phase change is not isothermal, but it occurs in a temperature range of few degrees. It could be 3, 5, but also 10-degree temperature range. Then sometimes we have supercooling. That is a phenomenon that may delay solidification and also alter the solidification temperature range of a lot of degrees sometimes, unfortunately. Then we have some hysteresis that can appear between charging and discharging, affecting the cycle symmetry. In some materials, we have degradation over time, long-term degradation that can sometimes dramatically alter the behavior over the cycles. And in addition, other parameters like cost, environmental and safety aspects, flammability, toxicity, chemical compatibility, that have to be considered, of course. So all these factors demonstrate why it's fundamental to validate the system also experimentally, because datasheets alone, unfortunately, are not sufficient. So we have to select a phase change materials. Usually, phase change materials are classified into 3 categories: organic, inorganic, and eutectic. Organic, such as paraffins, are chemically stable, show very little supercooling, but on the contrary, they have a very low thermal conductivity and sometimes they are flammable. We move to inorganic, the second group, such as salt hydrates. They offer very high, or well, relatively high with respect to organic thermal conductivity, latent heat, good volumetric density, but on the contrary, they suffer of a lot of supercooling, they are corrosive, and they are not very stable in time, so cycle after cycle. Finally, we have eutectic. Eutectic, well, can provide very sharp melting points and high energy density, but they are very expensive, and of course they are difficult to buy on the market, and at the moment they are less scientifically characterized, so we have very limited data of their behavior. Saying that, well, the choice between the families, it's not so straightforward, and it involves a trade-off between a lot of characteristics: performance, safety, durability, cost, and we don't have a unique answer. But latent storage is effective, and is particularly effective in application where the temperature control is important. For example, heat pumps and low temperature heating systems. Then also electronic thermal management, it's another case where latent storage makes sense. In fact, PCM can absorb the transient peaks of heat without large temperature rises. Then we have waste heat recovery that benefits from latent storage, especially when heat is available intermittently at a relatively constant temperature. Finally, also renewable energy integration can use latent storages to avoid oversizing the system. So in all these cases, the value of PCM lies in stabilizing temperature while managing energy flows. We want to focus on residential heat pumps. It's the focus of our project and also the focus of this speech. Residential heat pumps are highly efficient devices, but they have some constraints. They often operate under part load conditions and they experience frequent on-off cycling due to, well, mismatches between heat production and demand. So integrating phase change materials does not simply increase the storage capacity, but it modifies the overall system behavior. In fact, latent storages can reduce the compressor cycling, can stabilize the supply temperature, and can improve, for these reasons, the part load operations. Of course, these benefits are indirect, but they affect the entire systems, leading to an improved comfort, improved reliability, and maybe a longer component lifetime. Unfortunately, there are several common misconceptions about latent storages that I think it's important to clarify in a speech like this. So, phase change material doesn't automatically improve the heat transfer. We are dealing with material with very low thermal conductivity that can limit the performance, of course, if not properly addressed. Then we have that the temperature modification doesn't mean that all energy has been stored, because sometimes part of the PCM of the storage may remain solid or liquid if heat transfer is not optimized. We can buy some material that doesn't work if the geometry is not optimized. Of course, as we saw in the previous slide, PCM doesn't increase the efficiency of the heat pump by itself, but it reduces part load operation, the number of on-off cycles, and so on. So it's an indirect help to the heat pump efficiency. And finally, a larger amount of PCM, it's not always better. Sometimes it's a waste of money and space because excessive storage may reduce the responsiveness of the system or cannot be used by the system itself. So it's just a waste of space. So the key message is this one. The PCM is a design tool. It's not a magic solution, and it has to be integrated in the system. So from a design perspective, I think this is the most important part of the speech. The latent storage must be integrated as a part of the system from the very beginning of the project. Thermodynamic alone, it's not sufficient. Also, the material properties must be coupled with the geometry, with the operating conditions and the control strategies. Then we have also the heat exchanger design that is critical. Because with that, we ensure adequate charging and discharging of the whole material, of the whole PCM we have bought. Then the experimental validation is fundamental because the real behavior very often, unfortunately, deviates from the theory. So to conclude, I think that a successful latent storage design requires a system-level approach. And here are the take-home messages. Well, latent thermal storage exploits phase change. So they store and release large amount of energy at nearly constant temperature. The strength of this latent storage is thermodynamic, but the limitations are related to heat transfer for many reasons we saw in this speech. In residential heat pumps applications, PCM can help stability, flexibility, and also smarter operation. So the real value of these latent storages emerges only when the material, the system design, the control strategies are integrated. So a global approach is adopted. So before closing, I'd like to thank all the LIFE ITS4ZEB partners for their collaboration. But especially thank you all for your time and participation. If you'd like to know more, you can visit at our website, its4zeb.eu. You can follow us on social media, or you can subscribe to our newsletter to stay updated on the project's activities and all the upcoming events. From now, you can write your questions in the chat, and I'll be able to answer them. Well, we'll meet again soon for our next webinar, which will focus on latent storage systems, but on their applicative, under an applicative point of view. This was the thermodynamic, and we will move to the applications. Thank you again.